Welcome back to Summarize Science. Today, we're looking at a brand new study that uses the incredible James Webb Space Telescope to peer at a distant asteroid named Klio. Klio is part of a group called C-complex asteroids, which are like ancient time capsules from the early days of our solar system. They're especially interesting because they are rich in water and carbon-based materials, the very building blocks of life. Scientists believe these types of asteroids may have delivered these crucial ingredients to the early Earth. Klio is the biggest member of its own collisional family, a group of asteroids created from a larger body that was shattered long ago. Previous studies of this family showed that they're a mixed bag, compositionally, which makes Klio an intriguing target to understand the original parent body. Using JWST's near-infrared spectrograph, or NIR-SPEC, researchers captured the light reflecting off Klio in amazing detail. This is special because this specific wavelength of light is mostly blocked by Earth's atmosphere, making this kind of observation nearly impossible from the ground. One of the first challenges was to separate the reflected sunlight from the heat that the asteroid itself radiates into space. By modeling this thermal glow, they confirmed Klio is about 78 kilometers in diameter and is very dark, reflecting only about 5% of the light that hits it. This is the result: Klio's reflectance spectrum, basically its chemical fingerprint. That big dip you see around 2.8 micrometers is the star of the show. This specific feature is a telltale sign of hydrated minerals called phyllosilicates. Think of them as ancient space clays that formed when rock reacted with liquid water billions of years ago. To figure out exactly what kind of clays they are, the team compared Klio's fingerprint to various samples here on Earth. This included meteorites that have fallen to Earth, as well as pristine samples returned from the asteroids Ryugu and Bennu. The results were clear: Klio's spectrum looks very different from Ryugu and Bennu. Instead, it's a near-perfect match for a specific type of meteorite called a CM2 carbonaceous chondrite. This conclusion was even strengthened by looking at older data in the visible light spectrum, where the same CM2 meteorites were also the best match. The researchers also detected a smaller feature around 3.9 micrometers, which suggests the presence of carbonates. Interestingly, they couldn't find a clear signal for complex organic molecules, which might be because they are not abundant or have been degraded by space weathering over eons. So, what's the big picture here? This study gives us the first detailed look at the composition of asteroid Klio, thanks to the power of the JWST. It tells us that Klio is a water-rich world, similar in composition to some of the CM2 meteorites in our collections. This also confirms that it's a different kind of beast compared to asteroids like Ryugu and Bennu. By studying these different types of primitive asteroids, scientists can piece together a map of how water and other key ingredients for life were distributed throughout the early solar system. Each asteroid is a clue, and Klio is a very important one in solving the puzzle of our cosmic origins. Thanks for watching Summarize Science.